Assalamualaikum and salam sejahtera. We are from Group 7. Our group consists of 3 people. First, Muhammad Aiman bin Muhammad Safian. Second, Dennis Warren, anak lelaki Muthu Kumar. And the last one, Nur Fasha binti Muhammad Rashid. Introduction. A second-order differential equation describes a circuit of the second order. It is formed of resistor and two energy storage element worth of component which is RLC series and RLC parallel. The source-free series RLC circuit solution is referred to as the circuit natural response. The energy previously held in the capacitor and inductor rise the circuit. In a source-free parallel RLC circuit, all three components have the same voltage across them. The current passing through each element is exciting the top node in accordance with the passive sign standard. Any steady-state voltage or current in linear circuit with a sinusoidal source is a sinusoid. All steady-state voltage and current have the same frequency as the source.
So this is the first one, which is overdamped circuit. So the first thing we need to find is we need to find the resonant frequency, which is 500 rad per second. And then we find the damping factor value, which is 1000. So when the damping factor is greater than the resonant frequency, the circuit will be in overdamped condition. So the first thing we need to do is we need to find the S1 and S2 value. So after we got the S1 and S2 value, we just need to substitute into this voltage formula. And then we need to, we know the IO value is, I initial value is 20 milliampere. And after we got this equation, we can find the A1 and A2 values. So after that, we just do the substitution method and we got the A1 value is equal to negative 4.98 minus A2. And then we just do the differentiation to get the d per dt IL t equal to 10 over 400 milli, which is equal to 20 milliampere per second. So here is the equation, and then we sub the equation 1 into the equation 2, and we got the A2 value equals to 0.371 and A1 value negative 5.351. And then after we got the A1 and A2 value, we just substitute it into this formula. And to get the voltage equation, we just need to differentiate this current equation and multiply it by the inductor value. So for the critically damped circuit, the first thing we need to find is the resonant frequency, which is we get the value 333.33 rad per second and the damping factor 333.33. So when the damping factor and the resonant frequency is equal to each other, then the circuit will be critically damped. So as usual, we need to find the S1 and S2 value, and we got negative 333.33, and then we just substitute it into this formula. And as usual, we know because the question has given us the I initial value, which is 20 milliampere, and we just substitute into this formula to find the A1 and A2 value. So after that, we got the A1 value negative 4.98 and A2 negative 1.648 and 87. And then we just need to substitute the A1 and A2 value into the previous formula to get this equation. So to get the equation for VC, we need to differentiate the IL dt, and then we need to times it with the inductor value. So this is our equation, the last equation. So the next one will be the underdamped circuit. So here is the formula we use to get the resonant frequency values and the damping factor value. So the value for resonant frequency is 250 rad per second and damping factor 200. So when the value of damping factor is lower than the resonant frequency value, the circuit will be in underdamped condition. So here, the first thing we need to do is we need to find the S1 and S2 value. So after we got the S1 and S2 value, we just substitute into this formula. And then we just need to find the A1 and A2 value. So we need to differentiate the IL over dt. And then we need to find the value or equation when the time is 0. So after that, we got the A1 value equals to negative 4.98 and the A2 value negative 6.6. So after that, we just need to substitute the A1 and A2 into this formula to get this equation, the current equation. So to get the voltage equation, we need to differentiate this current equation and times it with the inductor value. So here is our final equation for the voltage. So this is the simulation for the overdamped circuit, critically damped circuit, and the underdamped circuit. So for the overdamped circuit, we use 50 ohm resistor, 10 microfarad capacitor, and 400 millihenry inductor. For the critically damped, we use 150 ohm resistor, 10 microfarad capacitor, and 900 millihenry inductor. So for the underdamped circuit, we use 250 ohm resistor, 10 microfarad capacitor, and 1600 millihenry for the value of inductor. So when we want to get the voltage plot response, we just need to drag the probe here into the analog transient. And then we just simulate the graph and we will get the result. So as we can see here, the green line represent the overdamped circuit, the red line represent the critically damped circuit, and the blue line represent the underdamped circuit. So to get the current plot response, we need to remove the probe in this analog transient, and then we just need to drop the probe inside this analog transient to get the plot response for time versus current. And then we just simulate the graph. And here, as you can see, the green one represents the overdamped circuit, the blue one represents the underdamped circuit, and the red one represents the critically damped circuit. So all of these three have their own response before they reach their steady state value.
Okay, so for question 2, for the project, we need to find IA, IB, IC, and VT value via the nodal and mesh techniques. We can use this Vs value for 100 sin omega t volt and current value for 10 cos omega t ampere. So we need to find this first. From given value from circuit, we can know the inductance value, resistance value, and capacitance value. So we can find impedance L1, impedance inductor 1 and inductor 2. It's also same as we can find the impedance capacitance 1 and 2 also. So the voltage Vt is equals to V4, Ia is equals to IL1, and Ib equals to IR2. So Ic equals to Ic1. For the nodal analysis, we need to find each node value. So we can find the V2 value for each node, node 1, node 3, node 4. So from all above V3, we can simplify it using matrix formation. So we can find the V1 value 10.008 volt, and V3 equals to 13.441 volt, and V4 equals to 64.5067. So this V4 is equals to V total. After that we can find the current value using V equals to IR, and then we use mesh analysis to find IA, IB, IC, and VT value. So this will be the loop 1, mesh 1, and this will be the mesh 2, and this will be the mesh 3. So we can construct a equation to find the output values. So this manual calculation answers is the same answer as simulations. So this is the circuit for question 2 project. So the value of current source is 10 ampere, and the frequency will be 1.591 kilohertz, and for the voltage source is 100 V peak, and for the frequency is same as current, 1.591 kilohertz. So I place these components in multisim. Okay, so let's run this simulation. Okay, let's see the IA value. So IA or IL1, I get 9.184 ampere. For IB or IRT, I get 2.889 ampere, and for IC or IC2, I get 5.629 ampere. So it's same as manual calculation. And for VT, I get 67.449 volt. Okay, for the graph, need to press simulate analysis, transient analysis. So the start time we need to be set 0, and for the end time need to set 0.05 seconds, and for the output we need to pick IA, IB, IC, VT. So we need to pick IC2, IL1, IR3, and V4, and simulate. So this will be the grapher view.
Discussion. In this case, the damping factor is greater than the resonant frequency. We may infer there will be two real numbers within a distinct negative real number. As a result, the reaction will be acidly damped as a result of overdamping. When the value damping factor A and resonant frequency are equally, the circuit will be critically downstate. From the observation, the voltage rises higher before the decreasing pattern appears. For the value IT, the value rises in a few seconds before the value becomes constant throughout the response. The response in the graph is an underdamped response. After a few seconds, the voltage value reaches the same value as the voltage source. For the value of IT, it rises at the beginning and slowly started to become flat as the time was increased. In conclusion, the second-order circuit RLC and pseudo-study statistic analysis project show that the project goals to apply circuit analysis methodology to the provide network issues using appropriate simulation is being achieved. With success in figuring out the second-order circuit current and voltage response. Following that, we are also able to solve the steady-state equation utilizing a variety of circuit analysis methods, including nodal analysis and mesh analysis. In addition, we can simulate steady-state current and voltage as well as second-order circuits. Finally, we can show that the steady-state analysis or simulation work for second-order circuit.